All right, hello. This is Adam Porter. This is Group 6, Part 1 demonstration code. I'm going to go ahead and share my screen here. All right, so this is the Part 1 demonstration for Lab 2. This is the rewritten program to include the nested subroutine calls inside the program flow instead of all the subroutine calls being in a series here underneath by the main label. So I've already gone ahead and I've programmed the microcontroller, I've started debugging, and I've properly built it. And I've also gone ahead and cleared out the values from the stack down here in memory so that they're not filled with any pre-existing values from the programming of the board. And so we can see it update in live time with what the values are being stored in the stack. As you can see here, we're pointing at the correct location to look at the stack because the stack pointer is looking at 8FF, and we're looking at the line down here starting with 8FE. So I'm going to go ahead and start stepping us through the code. We're going to go through we're going to start by going into the init subroutine. This is going to store the program counter of 102 into the stack because it's going to store the next program counter location. There we go. We can see the stack updating with 10102. We're going to go ahead and step through this. And then once we get to this next call, it's going to, since the stack pointer is looking at 8FD now, that's actually looking at these bits, these bytes right here. And so we're going to store the next memory location here, which is going to be 10C. And we're going to move into the getNums function, subroutine. And what this does is, as opposed to how the program was when all the calls were listed sequentially up here, we're going to start accumulating multiple values here in our stack that are all going to be processed at once in the end after we hit our returns. So we're going to go ahead and keep processing. Again, we're hitting another call, so we're going to add yet another value in there into the stack. I'm going to step us through our test functions real quick. Just for reference, our numbers we're dividing today are hex 88 and hex 44, which is 136 and 68 in decimal. And we'll look at the results after the program's done. So our values do not trigger any of the test cases. Dividend isn't equal to 0, divisor isn't equal to 0. They're not equal to each other, and dividend isn't less than the divisor. So we're going to go ahead and follow through with the divide subroutine, and we're going to get our final value that's going to appear here in our stack. So currently we have 1, 2, 3, 4 different program counter locations stored in our stack because we have called 4 different subroutines all nested within each other. We're going to go through here and divide. We're going to store out our values. And when we're going to start returning from our subroutines, and we'll watch the stack pointer as we do this. Right now, it's looking at 8F7, so right about here. And we're going to be returning with this first return function to program counter 130. So we're going to go here, we're at 130, and we're going to start working our way backwards because we're only hitting return functions from now on. So next we're going to hop to is 111. Then we're going to go to 10C. And finally, we're going to go back to 102. And there's our ending loop. So our division program ran correctly. We went through the nested subroutines. We accumulated some values within our stack, and then we returned from all those values all in a series at one time instead of going in and out, in and out. I'm going to stop sharing my screen now and end the recording. Thank you.
Hello, I'm Tomas. I am in Group 6, and this is Part 2. This is a bubble sort program that has 20 values in the flash memory, and the program sorts these values from minimum to maximum. And in this main, there are pointers that are initialized for data. There is a loop 1 here that takes the initial flash memory values and transfers them to the output table. The sorting starts down here. There is a second loop that is used for an outer pass that just iterates through this whole code. And there is a third loop that is smaller and is more focused in just comparing two values. So how this program works is the table is iterated through and each pair is compared, and the bigger number is swapped to the right if it needs to be swapped at all. So if that happens with this table of values, this is the output that will be sorted. So there is 3, 4, 6, 8, 11, and it goes on. So this output is in hexadecimal, so it does need to be converted to be understood. And this output is also stored in the SRAM or the IRAM.
This is part 3 of Lab 2 recording for the demo. My name's Alex and I'm part of Group 6, and this is my section. Here we have C code generated in Atmel or Microchip Studio. It is taking an unsigned character of global A, an unsigned character of global B with a value of 1, an unsigned character of value 2 of global C, and it is making global A set to the value of global C squared and subtracting global B from it. And so if we build this, it will then have an output file, which you can access over here in this section under the .lss file. If we go over here to the .lss file, this is the equivalent code in assembly. We have some code that runs beforehand, before the main code that executes. And then we have the main part, which is the unsigned characters and the calculations with them. So first here, we have some initializations of variables. We have the initialization of global A and B and C. And we have right here on this line is the XOR of register 25 and 24, which is the same thing as squaring it, because in register 24, there's a value of 2. And if you do an XOR with 2 in register 24 and the value in register 25, it will basically square the value in register 25. And it loads that here into 0, or it loads the value of global B into register 25, and then it subtracts 25, register 25 from 24, which is global B, from the squared value of global C. And then it stores that into register 24. And then here we have setting register 24 and 25 back to 0. And then it returns to the main function, clears the interrupt flag, and jumps back to the program and stops it.